This video looks at the concepts behind the two-factor ANOVA, a widely used technique which looks for associations and interactions between quantitative or qualitative factors and the means of groups that have different values of those factors. A lot of the concepts in the two-factor ANOVA build on the one-factor ANOVA, so I suggest watching this channel's videos about that technique before this video, especially the video that introduces the concepts. Assuming you've done that, or just want to focus on the two-factor ANOVA, let's begin. The scenario we're interested in is whether and how some factors we have identified influence or are associated with the mean values of groups that have differing values and combinations of those factors. We want to know if the values of a factor influence the means of groups that differ in that factor. Some examples of this type of question would be, do plants grow taller with different amounts of sunlight, or do plants grow taller with different fertilizer treatments? The values of the factors can be quantitative ones, like hours of sunlight ranging from 5 to 24 hours, or they could be qualitatively distinct ones, like fertilizer brand A versus fertilizer brand B versus brand C. We could use correlation or regression techniques, but there are many situations when nicely distributed data like this isn't available or even possible to obtain. Very often, we have data which comes from experiments with a limited set of different treatments or observed data which can only be grouped as categories, and this causes two problems. First, having such distinct sets of x values will often end up violating some of the assumptions of the regression and correlation techniques. Second, regression and correlation techniques are not useful for qualitative categories. If our fertilizer categories are brands, how would we plot these on a numerical x-axis, for example? We therefore need some other kind of technique for these situations. If you're familiar with the one-factor ANOVA, you might be asking yourself, why not just use the one-factor ANOVA? That technique allows us to identify when the values in different groups, defined by qualitative or quantitative categories, have different means. As a quick reminder, the one-factor ANOVA does this by looking at the variance between the means of the groups and the variance within the groups, and uses an F-test to see if the group means vary more from one another than expected based on the variation within the groups. If all we were interested in was a single factor, we could use the one-factor ANOVA, but only for one factor at a time, and that's the key. If we think about the scenario on the previous slide, we were thinking about both sunlight and fertilizer, two factors. If we did two separate one-factor ANOVAs, one for sunlight and one for fertilizer, we might have the same multiple comparison problem leading to extra type 1 errors that led us to use the one-factor ANOVA instead of t-tests in the first place. Whenever possible, we want to avoid using lots of tests. We prefer a single test that looks at the situation holistically. But even trickier, what if sunlight and fertilizer acted synergistically with one another so that the effect of sunlight depended on the fertilizer in some way? The two-factor ANOVA was developed to consider these two important types of questions that the one-factor ANOVA doesn't do a good job with. First, how might multiple factors influence or be associated with the means of the groups? Second, how might these factors interact with each other? That is to say, what if the factors are not independent? The answers will come from the two-factor ANOVA. To answer the first question, we can estimate the effects of each separate factor by considering them independently and one at a time. To answer the second question, we'll estimate how much of the pattern isn't explainable by the factors independently and is therefore due to an interaction. Before continuing, it's useful to think about the similarities and differences for the one-factor and two-factor ANOVAs. The two different ANOVA techniques have a number of similarities in terms of the calculations that are done. The two-factor ANOVA uses many of the same steps as the one-factor ANOVA, calculating several sums of squares values, identification of appropriate degrees of freedom for different groups, using these two values to calculate mean sums of squares, conducting F-tests, and making a figure to interpret any statistically significant results. The two different ANOVA techniques differ in their purpose, however. For the one-factor ANOVA, the goal is to determine if any group means differ. The main purpose of this technique is that it solves the type 1 risk problem arising from multiple comparisons when doing pairwise tests. For the two-factor ANOVA, the goal is to determine if there are any non-random associations or relationships between factor values and the data, not just to determine whether individual group means differ from each other. While the two-factor ANOVA also solves the type 1 risk problem from multiple comparisons when looking at the two factors, a critical additional benefit is that it also allows discovery of non-independence, that is, interactions, between factors. This non-independence can often be one of the most interesting things to learn about the system we're studying. In the same way that visualizing the distributions of data was helpful for understanding how the one-factor ANOVA works, let's look at what the two-factor ANOVA is doing visually. Imagine a scenario in which we have 6 groups, 3 different colors, green, purple, and brown, and 2 different shades, light and dark. The top diagram shown depicts this situation, where we can see the distribution of values for each combination of these factors, with the x-axis representing the values in the datasets. The bottom diagram shows the bar charts corresponding to the means for each combination. In this case, the y-axis represents the mean values for the 6 groups. It might be worth it to pause at this point and take a good look at these diagrams to make sure you understand how they're showing the exact same information, just in different ways. Focusing on the top diagram, visually we can see that if we look at the color factor, green groups have smaller means than purple groups, and purple groups have smaller means than brown groups. Also, the means of the groups with the light shade factor are smaller than the means of the groups with the dark shade factor. Since we're doing an ANOVA, we'll be using the sums of squares and variances and comparing them to identify when the means of the groups, more precisely sets of groups, differ more from each other than expected from the variance within the groups. Keep in mind that mean sums of squares and variances are the same thing. The basic idea is the same as for the one-factor ANOVA, but instead of comparing a single mean sum of squares among to the mean sum of squares within, we'll have mean sums among for the two factors and an interaction. Okay, so how do we calculate the sums of squares for this ANOVA? First, the sum of squares total and sum of squares within will be calculated the same way as we would for the one-factor ANOVA. Then for the sum of squares among for the color factor, we group the colors together and consider 3 groups, one for each set of groups that have the same color factor value, and calculate the sum of squares based on these 3 values. Then, for the sum of squares among for the shade factor, we group the shades together and consider 2 groups, one for each set of groups that have the same shade factor value, and calculate the sum of squares based on these 2 values. Finally, the sum of squares among interaction value will come from the equation sum of squares total equals sum of squares among for color, plus sum of squares among for shade, plus sum of squares among for the interaction, plus sum of squares within. The overall variation seen arises from 4 sources: the effect of each factor, their interaction, and the noise or variation within each group. Let's look at this scenario again, but now adding in a view of the data table. Each column represents values of the color factor, and sets of rows represent values of the shade factor. The overall data table would have 6 sections, one corresponding to each combination of the color and shade factor. We can look at how the bar chart of the mean value for each group corresponds to each part of the data table. So we organize our data as shown, and then we can start thinking about how we would calculate the sums of squares terms we just talked about, the sum of squares total, sum of squares within, and the sum of squares among terms for each factor and the interaction. For the sum of squares total, we treat all data values as if they were from one big group. Then we calculate the sum of squares of this one large set of numbers. This is a measure of the total variation, which will be broken down into subsets as we look at the other sums of squares. This sum of squares value is the SST. For the sum of squares within, we treat each combination of factors as its own separate group, as if we were doing a one-factor ANOVA. We calculate the sum of squares separately for each of the 6 using their own group mean, and then add these together. This sum of squares value is the SSW. How are the means of groups associated with different values of the first factor? For the sum of squares for the color factor, we treat each color as its own group, ignoring the shade factor. Then we calculate the sum of squares for each of the 3 groups which differ in color, and then add these together. We also multiply by the sample size in each color to take this into account. This sum of squares value is the sum of squares among for color, the sum of squares among for the first factor. Now for the second factor. How are the means of groups associated with different values of the second factor? For the sum of squares for the shade factor, we treat each light or dark shade as its own group, ignoring the color factor. Then we calculate the sum of squares for each of the 2 shade groups, and then add these together. Again, we multiply by the sample size in each shade to take this into account. This sum of squares value is the sum of squares among for shade, the sum of squares among for the second factor. Finally, for the third sum of squares among factor, the one representing the interaction between the 2 factors. This estimates how much the factors interact with each other in terms of the means of groups with combinations of the factors, deviating from what we would predict thinking about the 2 factors independently. There are 2 options for this. First, we can use the fact that the 3 sums of squares among terms and the sum of squares within add up to the sum of squares total, so we can subtract all the others from the sum of squares total to solve for the sum of squares among interaction term. Second, we could treat each combination of factors as its own group and then calculate the sum of squares for each of the 6 by comparing each group's mean to that expected from the individual factors and the overall mean. This also gets weighted by the sample size for each of the 6 groups. This is much more complicated, so the first approach is much more common. Here's an overview and quick recap of how these things are related. This diagram shows conceptually how the sums of squares terms contribute to the sums of squares total, the purple arrow. This is the equation that relates the sums of squares values. We can see how the 3 sums of squares among terms and the sum of squares within term mathematically add up to the sum of squares total, the overall sum of squares. To calculate these values, we arrange the data in a table with columns for one factor and sets of rows for the other. We calculate sums of squares for all values, comparing them to the overall mean when calculating the sum of squares. We calculate the sum of squares within values separately for each group using the group means, then sum them all. We calculate the sum of squares values for each factor value, comparing the groups with the same factor values to the overall mean, then sum them and weight by the sample size for each factor value. We calculate the sum of squares for the interaction by using the equation relating all the sums of squares terms. This is where the sums of squares values come from. But what about the mean sums values we need for the f-tests we'll be using to test for the significance of our two factors and their interaction? When testing for significance, we'll use f-tests. Let's continue with the previous example, and let's use j equals 3 for the 3 color factors, and k equals 2 for the 2 shade factors. Just like with the one-factor ANOVA, we compare the mean sums for the factors and interaction to the mean sums within using an f-test. To get mean squares, we divide the sums of squares that we've already described by the degrees of freedom. We'll be comparing each mean sum among to the mean sums within, so let's look at that first. The degrees of freedom for within is the number of values in each group minus 1, which would be the total number of values minus the j times k number of groups. The mean sums within is therefore the SSW divided by n minus j times k. Let's call the first factor factor A, which in our example is the color factor. The degrees of freedom we would use to get the mean sum among for factor A would be j minus 1, since there are j categories for factor A, the color factor. The mean sum is the sum of squares divided by this. The f calculated value would be the mean sums among for factor A divided by the mean sums within value. Let's call the second factor factor B, which in our example is the shade factor. The degrees of freedom for factor B would be k minus 1, since there are k equals 2 categories for factor B, the shade factor. As before, the mean sum is the sum of squares divided by this. The f calculated value would be the mean sums among for factor B divided by the mean sums within value. For the interaction, the degrees of freedom would be j minus 1 times k minus 1, similar to what we might expect in a chi-squared test of independence with a 3x2 contingency table. The mean sum is the sum of squares for the interaction divided by this. Just like for the separate factors, the f calculated value would be the mean sums for the interaction divided by the mean sums within value. With these three f values, we can do 3 f-tests to determine the significance of each factor individually and for the interaction between them. Just like with the one-factor ANOVA, the results are usually presented in an ANOVA table with columns for the calculated values and rows for the sources of variation. We fill the table up with the values we calculated and use the calculated f-values to perform f-tests to get p-values for each factor and the interaction. These p-values indicate any significant associations between factors and the means on their own, and if there's a significant interaction between the factors. It's useful to visually remind ourselves of what the values in this table represent. The mean sums, or variances, of the group means relative to the variance within the groups when considering the factors individually and in combination. The p-values in the table only tell us whether something non-random appears to be going on for the factors or interaction, but they don't tell us what the pattern is or what the nature of the interaction may be. For that, we need to make a pair of figures called interaction plots. The ANOVA analysis provides information about whether factors, and the interaction between them, are significant, but not what those effects are. Do the means get larger as a factor changes, or smaller, or up and then down? Do the two factors act synergistically, or does one temper the effect of the other? To visualize this, we make a pair of interaction plots using the mean values of the groups. Each plot uses the values of one of the factors on the x-axis and plots the group means on the y-axis. The second factor is represented by symbols within the figure. So let's think about our data for the means of groups with the 3 values of the color factor and 2 values of the shade factor. The first interaction plot would put the color factor on the x-axis, and for each of these we would have 2 values, the light and dark values for the second factor shade. The values of 4 and 6 for the 2 green groups will be shown as a circle and diamond for the light and dark groups above the x-axis location for green. The values of 14 and 16 for the 2 purple groups will also be shown with a circle and diamond for the light and dark groups above the x-axis location for purple. Lastly, the values of 23 and 25 for the 2 brown groups would be shown the same way. To help visualize the means for the groups with the same shade factor, we use the same symbol or color and connect their values with lines. We can see from this that as we move from green to purple to brown, the means seem to increase. This is the sort of pattern that would be consistent with the color factor being significant. Whether the apparent pattern is genuine and significant or just random requires reference to the p-values from the ANOVA table. Interaction plots often don't show how much variation there is in each group, unlike the left-hand plot showing the means and standard errors. If the standard errors were much larger, a situation in which the pattern may be just due to random chance, the interaction plot would still look the same. This interaction plot is great for visualizing the effect of the factor on the x-axis, color, but that's just one of our factors, so we typically also look at a second plot with the other factor on the x-axis. Now, each shade value on the x-axis has 3 values associated with it, one for each of the values of the color factor. The values of 4, 16, and 23 for the 3 light groups are shown, along with the 6, 16, and 23 for the 3 dark groups. We use 3 different symbols or colors and connect the points corresponding to the same value for the color factor. On this second plot, we can see from this that as we move from light to dark, the means seem to increase. This is consistent with the shade factor being significant, but again, we would need to check the ANOVA table to confirm whether this is a significant pattern or easily caused by random noise. This interaction plot is best for visualizing the effect of the shade factor. To visualize any interaction effects, we look at the lines connecting our symbols to see if they're all parallel. Parallel lines indicate a lack of any interaction, but if the slopes vary, this indicates that the effect of the x-axis factor may change depending on the value of the other factor. In this plot, there is no visual suggestion of an interaction. The 2 factors seem to have independent effects. Let's look at a few examples of interaction plots and make guesses about what we would expect the ANOVA table results to be. This pair of interaction plots is the one we just looked at. Based on just these patterns, if we didn't have ANOVA table data, we would probably guess that the color and shade factors would be significant, but the interaction would not. These interaction plots seem to show no real effect of the color factor. There's no overall trend as we move from green to purple to brown. There does seem to be an effect of the shade factor, however. For the interaction, it sort of looks like the effects of going from green to purple depend on the shade. If the shade is dark, the means decrease, but if it's light, they increase. While the lines are not parallel, they're only slightly different, so it's hard to know whether the interaction would be significant or not. It's cases like these where the ANOVA table is most important. For these interaction plots, the color factor looks significant, and there seems to be a clear interaction as well. Light versus dark seems to have very different effects depending on the color. This is most obvious in the right-hand plot. The overall shade factor by itself doesn't seem to do much though, but maybe there's a slight upward trend from light to dark, hard to tell. This is another situation where the ANOVA table is critical. In this case, the color factor doesn't look significant, and there appears to be a clear interaction, seen in either figure fairly clearly. The shade factor looks significant, but we would always want to check the ANOVA table just in case. Now let's look at an example which combines the ANOVA table and interaction plots. Imagine a company develops a novel type of fertilizer that they wish to test. They raise plants under 3 light levels with 2 types of fertilizer, the novel fertilizer and a previous formula. The light level and fertilizer formula are the 2 factors. They measure the heights of 4 plants with each combination after 30 days. This will be the metric whose mean we're interested in. Is the mean height associated with the light and/or fertilizer individually, and is there an interaction between the 2? Let's assume the ANOVA table and data look like this. The figure makes it look like the amount of light is associated with the height. The more light, the taller the plants. It also looks like the novel fertilizer is associated with a taller height. The confidence intervals overlap though, so maybe these patterns aren't statistically significant. The ANOVA table indicates that there's a significant association between height and the fertilizer treatment. This comes from the p-value being less than 0.05. However, there is no significant association between height and the amount of light because the p-value is larger than 0.05. There's also no significant interaction between fertilizer and light. The factors act independently, as indicated by the p-value larger than 0.05. This is what the interaction plots look like. We can see an apparent upward trends in the means associated with the amount of light. We want to mentally think about combining the 2 fertilizer treatments as shown by the yellow clouds and line to visualize this. The ANOVA table tells us that this apparent trend is significant. We also see what appears to be an upwards trend in the means associated with the fertilizer treatment. Now the yellow cloud and line represents combining the 3 light treatments. However, the ANOVA table indicated that this wasn't significant. The parallel lines in the interaction plots are consistent with the very high p-value for the interaction term, indicating no interaction between the light and fertilizer factors. We can consider them separately from each other. This is the same scenario, but I changed the data behind the scenes so that there's less noise in each group. The means are unchanged, but the smaller SSW value increases the F values, and now both factors are significant while the interaction remains non-significant. The interaction plots would look identical with the same general trends. But now both of the apparent trends are non-random and would represent genuine biological processes having to do with light levels and different types of fertilizer being associated with taller or shorter plants. In fact, if we've set this up carefully in an experiment which controls all the other variables like humidity and genetic differences between the plants, we could argue convincingly that the light and fertilizer differences caused the observed height differences. This is the same light and fertilizer scenario, but I've changed the data so that there isn't a significant association between either fertilizer or light and the height of the plants. Both of these p-values are larger than 0.05. However, in this data I've added a significant interaction, which we can see a bit easier in the interaction plots than in the bar chart. The high light treatment with the novel fertilizer is less than we might have expected based on the first two light treatments. There's something about the combination that results in an unexpected value. Let's look at another case. Now imagine a study on the effects of different amounts of fertilizer and how the effect might depend on the amount of water. Plants are raised under 3 water levels with no fertilizer, some fertilizer, and extra fertilizer. Heights of 4 plants with each combination, for a total of 9 times 4 equals 36 plants, are measured after 30 days. Is the mean height associated with the amount of water and/or fertilizer individually, and is there an interaction between the two? And assuming this is a highly controlled experiment, where the only difference between these sets of plants is the water and fertilizer levels, we can make conclusions about causes, not just associations or correlations. Let's assume the ANOVA table and data look like this. This data is a bit messier than the previous example. There is no significant association between height and the water treatment, since the p-value is larger than 0.05. All by itself, increase in the water doesn't alter the heights of the plants in these fertilizer treatments. However, there is a significant association between height and the amount of fertilizer because the p-value is less than 0.05. There is also a significant interaction between water and fertilizer, as indicated by the p-value smaller than 0.05. This is what the interaction plots look like. We can think about the two upwards trends for the separate factors, but must keep in mind that only the trend for the fertilizer amount is significant. The interaction seems to be a situation in which the highest amount of water, combined with extra fertilizer, resulted in shorter plants than expected from thinking about the effects of each separately. This is the same scenario, and I've used identical data values behind the scenes to generate the ANOVA table, but with double the sample size, 8 plants per group instead of 4. All the sums of squares values will be twice as large, but the degrees of freedom values total and within will be more than doubled. The effect of this is to double the mean sums among values, while the mean sums within value get slightly smaller, resulting in much larger f values, and now all 3 p-values are less than 0.05. In fact, we would probably state that the patterns seen for the fertilizer treatments and the interaction are now highly significant and extremely convincing. Our overall conclusion changes now. The apparent trends seen for both factors are significant, and so is the interaction. If this was real data, the increased sample sizes allow us to avoid making the type 2 error we made with the smaller sample sizes. We previously missed the biological effect where increased amounts of water increased the height across all fertilizer treatments in general. This is just one example of the importance of making sure to have sufficient sample sizes when designing experiments. It costs more money, but reduces the risk of type 2 error. In fact, the first step in designing many studies is to make sure we have sufficient sizes to detect the trends or patterns we would consider relevant or meaningful. There are a couple of important cautions about the two-factor ANOVA that are essential to keep in mind. First, ANOVA techniques are homoscedastic. The variances in each group must be equal. We therefore have to do an Fmax test before beginning, just like we need to do when using the one-factor ANOVA technique. If the groups don't have equal variances, the two-factor ANOVA can give incorrect results. Second, a significant association or relationship between factors and the means of groups does not prove direct causation. Importantly, this does not mean that a significant association is useless. There's a well-known line that correlation doesn't imply causation, but it's a common amateur or beginner mistake to interpret this to mean that significant associations don't show anything. A significant association or relationship doesn't prove causation, but it does show that something interesting is going on that connects the factors and means in some way. If other factors have not been controlled, for example a field or epidemiology study, the ANOVA just demonstrates a connection of some kind. It may be one factor directly causing the other, indirect causation, or a third factor influencing both. Exactly what's going on is unclear, but something is connecting the factor and the measured values. On the other hand, if all other factors have been controlled, for example a highly controlled experiment which changes just those two factors while keeping everything else the same, then the ANOVA can demonstrate causation. This may still be indirect. There may be some intermediate steps between the factor and the measured value, but the factor is ultimately responsible for influencing the measured value. They're not just associated statistically because they're both responding to something else. Let's sum up how we use the two-factor ANOVA approach. Here's the question we're seeking to answer. Is there an association between two factors and the means of groups that differ in the values and combinations of the factors? The factors can be either numerical or categorical. The approach to answer this will be an analysis of variance, which is abbreviated as ANOVA, and this will be a two-factor ANOVA because we're interested in two different factors which may influence the means, as well as any interaction between them. As with the one-factor ANOVA, a prerequisite for doing the two-factor ANOVA is the equality of population variances, which we would typically test using an F-max test. The conceptual null and alternative hypotheses are that there are no associations or interactions relating the factors and the group means versus at least one association or interaction between the factors and the means. We don't actually test those hypotheses. We instead test a set of three hypotheses about the relative magnitudes of three mean squares among terms and the mean squares within term using F-tests. To do a two-factor ANOVA, we therefore have 5 steps. Step 1. Perform an F-max test to ensure equality of variances. Step 2. Calculate the full set of sums of squares terms and identify what the degrees of freedom are for each factor and the interaction. Step 3. Complete the ANOVA table by using the values from Step 2 to calculate the 4 mean sums, and then do the 3 F-tests, one for each factor and the third for the interaction. We use the p-values from those F-tests to reject or fail to reject each null hypothesis. Step 4. If any null hypothesis is rejected, we would create a pair of interaction plots to interpret what the significant results mean for the associations between the factors and the measured value, and what any interactions between the factors look like. Step 5 is to always be careful with the interpretations. Significant associations indicate that something is going on, but we have to think carefully about the nature of the data to understand the nature of the causality so we don't overinterpret our results. If you're still not sure how this would be used in practice, the Worked Examples video has 2 more scenarios with step-by-step calculations from full datasets. The entire process of the calculations is demonstrated, as well as the interpretations discussed. As per usual, a high-resolution PDF version of this full set of slides is available on the StatsExamples website. Also per usual, like, share, and subscribe if you found this video useful or you think that others might as well.